Welcome to ChemExam Explained, where the aim is chemistry clarity, exam mastery. In today's video, we will be looking at CSEC Chemistry, May-June 2012, question number 1. That is data analysis. This topic is on rates of reaction. Let's go. 1A. A student conducts an experiment to investigate the effect of particle size on the rate of reaction between calcium carbonate and nitric acid. He weighed 1.8 grams of powdered calcium carbonate and 1.8 grams of large granules of calcium carbonate, that is the marble chips, and allowed each to react with excess dilute nitric acid. The volume of gas produced at 10-second intervals was measured for a total of 100 seconds. Table 1 is a record of the volume of gas produced from each set of reactions with the powdered calcium carbonate and with the marble chips. Figure 1 is an incomplete diagram of the arrangement of the apparatus used in the experiment. Figure 2 shows the graph obtained for the rate of production of gas from powdered calcium carbonate. So here you have the table showing the results using the powdered calcium carbonate and the marble chips, and here you have the incomplete apparatus. You should have the graph here, and you will be required to plot another set of results, another graph to show what's going on between the chips and the powdered calcium carbonate. So the first question is to complete figure 1 to show how the gas was collected and measured during the experiment. So what's important is to make sure we have a gas syringe along with a delivery tube. We must have a rubber bung. And of course, this will collect the gas and it will be measured with the syringe. You must make sure you have your graduated marks on the syringe and it is able to slide in and out, right? Because as the gas is produced, it will push the syringe out and you can now make your measurements from the marks. So this is important. So this is figure 1. 1A part 2. Using the same axis in figure 2, plot a graph of the volume of gas produced versus time for the reaction with marble chips. 4 of the points have already been plotted on the graph. So if you notice, this is the first graph that was plotted for us, and we are to plot this graph here, and you can see that 4 points were done for you already. So you are to complete those points. And of course, if we use on the x-axis 10 units for every 2 centimeter, and so you know that each of these small boxes here would be 1. So right here will be 5, then 10, 15, 20, and so on. And of course, you'll see now on the y-axis, 50 units for every 2 centimeter. So right here would be 25, 50, and so on. So if you want to know the value of each of the small boxes, you would divide 50 by 10. So 50 divided by 10 would give you the value of one of the small boxes here. So you can do your plot. And when you finish with your plot, it should look like this. 1A part 3. With reference to the volume of gas produced and the slopes along the 2 curves on the graph, outline one similarity and one difference in the volume of carbon dioxide produced from powdered calcium carbonate and from marble chips. Include a reason in each case. So let's start by looking at the similarity and then the difference. So the similarity is that the total volume of carbon dioxide produced was the same for powdered calcium carbonate and marble chips. This is because the mass of calcium carbonate used for both reactions is the same. That is, both use 1.8 grams of calcium carbonate. So what we're saying here is we use 1.8 grams of calcium carbonate in the powdered form and 1.8 grams of calcium carbonate in the marble chips form. Let's now look at the difference. The graph for the reaction with powdered calcium carbonate has a steeper slope than that of marble chips at the start of the reaction. This is because the rate of reaction for powdered calcium carbonate is faster, since the total surface area of the powdered calcium carbonate is greater than that of marble chips. So we know that surface area would increase the rate of reaction. And how do we know that it is faster? The steeper the curve, the faster the reaction rate. So this one here at the top is faster, and this one is slower. So this one would represent the powdered calcium carbonate, and this one would represent the marble chips calcium carbonate. 1A, part 4. Write a balanced equation for the reaction between calcium carbonate and nitric acid. So to help with writing the equation, let's start with a general word equation. So of course, we'll start with a carbonate and an acid, and it would react to form salt, carbon dioxide, and water. So in this case, our carbonate is calcium carbonate, which is in the solid state. We have our nitric acid in the aqueous state. When they react, it will produce the salt, calcium nitrate. Of course, it is aqueous because all nitrates are soluble, plus water, which is a liquid, and carbon dioxide, which is a gas. Question 1A, part 5. Calculate the volume of gas that can be obtained from reacting 1.8 grams of calcium carbonate with dilute nitric acid at RTP, which is room temperature and pressure. So we're given some values here. We have that 1 mole of a gas occupies 24,000 cm cube or 24 dm cube at RTP. We have the relative atomic masses of the elements carbon to be 12, oxygen 16, and calcium 40. Let's start with our calculation. Let's first identify what we want to find. We want to find the volume of gas that can be obtained from the 1.8 grams of calcium carbonate that reacted with the nitric acid. And of course, it is at RTP, room temperature and pressure. So the first thing we notice is that we have the mass of calcium carbonate. So what we're going to do here is to use the mass to find moles of calcium carbonate. So we're using mole equal mass over molar mass. So in order to find the moles of calcium carbonate, we're going to be using the mass of calcium carbonate given in the question divided by the molar mass of calcium carbonate, which is 100 grams per mole. So we say 1.8 grams divided by 100 grams per mole, and our answer is 0.018 mole. So this is the mole of calcium carbonate. If you look back at the equation, we must look at the mole ratio between the calcium carbonate and the carbon dioxide. So you see that we have carbon dioxide here and we have calcium carbonate here. What is the mole ratio? Because the equation is balanced. So the mole ratio is 1:1. So what does that mean? Once we know the moles of calcium carbonate and the mole ratio is 1:1, then we know the moles of carbon dioxide. So we can say the calcium carbonate to carbon dioxide is 1:1. So whatever the moles of calcium carbonate is, that is equal to the moles of carbon dioxide, since the mole ratio is 1:1. So now that we know that the mole ratio is 1:1, we can now make the statement that the moles of carbon dioxide is also 0.018 moles. So we are now going to find the volume of carbon dioxide from the moles of carbon dioxide. So we know that moles of carbon dioxide is equal to the volume of carbon dioxide in dm cube over the value at RTP. So we are now going to use moles is equal to volume in dm cube over the value at RTP, which is 24 dm cube per mole. Now notice, if we are using the volume in cm cube, then we can use 24,000 cm cube per mole. But I think it's easier if we go with the volume in dm cube. So we're going to now make volume the subject of the formula. So volume is equal to moles times the volume at RTP. All right? So it's dm cubed per mole. And the unit for mole, of course, is mole. So when mole cancels mole, your volume should be in dm cubed. So what we're doing now is plug in the value for the moles of carbon dioxide, which was 0.018 mole, and we put in the volume for 1 mole of gas at RTP, which is 24 dm cubed per mole. When we multiply that, we get 0.432 dm cubed. Again, you could work your values in cm cube and then convert at the end. All right? So if we have 0.432 dm cube, we can convert back that to cm cube by simply multiplying by 1,000. So 0.432 times 1,000 equal 432, and this would be in cm cube. 1A, part 6 and 7. Let's look at part 6. From the graph, the total volume of gas produced is 370 centimeters cubed. Suggest a possible reason for the difference in your answer obtained in part 5 on page 4 and the volume of gas obtained from the graph. So let's come back here and just make sure that we're on the same page. The volume we got from our calculation was 432 cm cubed. And the volume from the graph was 370, right here at the top. All right, so that's what we're looking at. So we are comparing the volume of 370 produced from the graph and the calculated volume of 432 cm cubed. So you realize that from our calculation, we produced a greater volume of gas than that was produced from the graph. So we're saying that a possible answer for that could be, for part 6, that possible impurities present in the calcium carbonate used. Part 7, state 2 other factors than the one given in part 6 above that can affect the rate of reaction between nitric acid and calcium carbonate. So we know that you have several factors that can affect the rate of a reaction. So 2 others, apart from the one given in part 6, could be the temperature as well as the concentration of nitric acid. So we know that if the temperature is high, then the rate of reaction would be high. If it's low, the rate is going to be slow. And if the concentration of the nitric acid is high, that should contribute to a faster rate. And if it is low, it should contribute to a slower rate of reaction. Question 1, part B. A student conducts a number of tests on a solution of compound Y. Some of the observations and the inferences made from these tests are recorded in Table 2. Complete Table 2 by writing in the observation and inferences numbered 1 to 5. So here we have Table 2. You'll notice that we have all the tests. We have some observation, and where we have the observation, we are to complete the inference. And in the other areas, we have the inferences given already, and then we are going to give the observation for that inference. So let's continue. For test 1, aqueous sodium hydroxide is added gradually until in excess. The observation was a red-brown precipitate that is insoluble in excess sodium hydroxide is formed. All right, so we're saying that when you form that red-brown precipitate, that precipitate will not dissolve in excess sodium hydroxide. And that, of course, can only be iron 3, because iron 3 is the only colored substance that gives you red-brown, and it is insoluble in excess. If it was copper, it would be blue. If it was iron 2, it would be dirty green. or pale green. So iron 3 plus aqueous ions are present. So Fe3 plus. Test 2. A strip of magnesium ribbon is added. So let's look at this part first. So the inference is the magnesium reduces solution Y. Iron 2 ions are produced. So we're saying that when we have our solution Y, which contain iron 3, of course, we add the magnesium strip or ribbon. It reacts with the iron 3 solution, and there's a color change from red-brown to pale green, since the magnesium reduces solution Y, which was iron 3. So iron 3 was red-brown, and if it is reduced to iron 2, it will go from red-brown to pale green. And so when you have the reaction, the magnesium dissolves because it is reacting. So in this case, when we say dissolve, it is not dissolving in terms of the physical change. A better term would be it disappears, since we know that dissolving is a physical change. So it reacts with the aqueous iron 3, and then it forms aqueous iron 2 ions. So for the next part of the test 2, aqueous sodium hydroxide is added to the mixture until in excess. So we're adding aqueous sodium hydroxide in excess to the mixture that contains iron 2 ions, and that will give us a green gelatinous precipitate. So when we add the sodium hydroxide in excess to the solution that contains the iron 2 ions, you form a green gelatinous precipitate. And that precipitate, of course, is iron 2 hydroxide. This will be insoluble in excess. That is, it will not dissolve when the excess sodium hydroxide is added. And so we can write the balance equation that we go from iron 2 plus aqueous along with the OH minus ions from sodium hydroxide to produce iron 2 hydroxides, which is a solid, and that is why it is a precipitate. So this is your green precipitate. Test 3. Dilute nitric acid is added followed by barium nitrate solution. So once you see dilute nitric acid followed by barium nitrate, or dilute hydrochloric acid followed by barium chloride, we are testing for the presence of carbonates, sulfates, and sulfites. So if our observation when using these reagents is that no precipitate is formed, then we can come to the conclusion that no carbonate ions, no sulfite ions, or sulfate ions are present. Test 4. Silver nitrate is added followed by aqueous ammonia. So once you see these reagents, silver nitrate followed by aqueous ammonia, we are testing for halide ions. In this case, the inference is that chloride ions are confirmed, which is suggesting then that we must get a white precipitate which dissolves in the aqueous ammonia. If it was Br minus ions present, then we would get a cream or a off-white precipitate. All right, and that would dissolve partially. And for iodide ions, we would get a yellow precipitate which will not dissolve in the excess aqueous ammonia. This is the end of CSEC Chemistry, May-June 2012, question number 1. Please remember to like, subscribe, and click the notification bell so that when new videos are uploaded, you will be notified. Thank you.